Another example. Estimating the probability the system fails before t, and t is a large time. T is a small time. Yeah, t is something that is not too large. Okay. Estimating the probability the system fails before t. Suppose x is an exponential random variable. So the probability, okay, again, this is a toy example, right? You don't have to do this. You don't have to estimate because you know you can compute. But I'm using a toy example to quantify the effect of the variance reduction achieved by this new technique. Okay. All right. So t is something you set. Consider a g, which is another exponential with a different rate. Right now, x has a rate of lambda. Consider a different distribution g that is also exponential but with a different rate. So it's very similar to the idea on the previous page for the previous example. Original distribution is a normal 0, 1. We tilt the distribution, we change the distribution to a normal mu1. We maintain the form, it's still normal. Here, original distribution is exponential, we change it to a new exponential having a different rate. Okay. So this is the important sampling estimator, recall, here. The important sampling estimator, basically what I take from the right hand side, what's inside the expectation. That is the h function, whatever h function you have. In many cases, this h function is the indicator, times the L function, which is the ratio between f and the g. Okay. Come back here. So h times L, right? But a y follows g. H, y, f, y over gy, right? How would you estimate this probability? Well, you would, the crude Monte Carlo simulation would be this, indicator, right? So that's h. F is the original distribution with lambda, and the g is the new distribution with lambda tilde. You can combine things and a little bit, you get this. Okay. That's this, right? Let's estimate the variance of the important sampling estimate. Let's estimate the variance of this guy. In this case, we can compute it. We're able to compute it. Okay. To compute the variance, let's compute the second moment first. We don't have to compute the first moment because we know this is an unbiased estimator. We know the mean is equal to this. Let's compute the second moment. So that's the second moment, right? So expectation of this guy. Okay, of course, this expectation is taken with respect to y now. Right? This is y. Oh, I am making a mistake. This should be y. Should be y here. So once you talk about this important sampling estimator, you no longer have x. Everything is changed to y. So it's y here, right?